Hi everyone, welcome back. In this video, I wanted to show you how you can extract some details regarding the back end of line or BEOL of a given process, fabrication process. Essentially, we need to extract these three files. So we have like two files really, a TECH file and an AMAT file. So these two files will be very useful to us when we want to go between Cadence and HFSS and simulate passives like antennas, transmission lines, inductors, and so on. And we need to extract these files, create these files really from data that is extracted from the PDK. So it's a very useful step to do whenever you're trying to set up a new PDK for a high frequency kind of tape out. So I wanted to show you how to do that. Okay, to get started, all we need to do is open up the PDK. Typically in the documentation, you'll have several different files. So this is for the GPDK that Cadence provides. And one of these files should contain the different layers and the layer dielectric constants, thicknesses, and even the metals, metal sheet resistance, and so on. So in this case, it's in the DRC file, but in your PDK, it may be in a different file. So go through your PDK and try to find that. So let's open it up. So here you see that at the end of this file, there's all this information, right? So what we care about is this part, this page and the previous page actually. So on page 104 of this process, we see that we have the layers, the layer thickness in angstroms, and the layer dielectric constants, right? Which is given by K. Okay, so this information is very useful. It also provides the different sheet resistances for all the metal layers and also for the via layers. So it's exactly what we need. So we'll use all this information to create the AMAT file and the TECH file, which will be very useful to us. Okay, so how do we go ahead and do that? So here I've made an Excel sheet, and I usually do it this way, but you can do it a different way if you like, where I have the dielectric layers listed out. So I'll tell you what these layers mean, and also the metal layers listed out. So if we go back to the PDK, we see that the first layer is shallow trench isolation STI, or the field oxide layer, FOX. And if you want to know like what these layers are and how they're exactly formed, there is a good reference that I recommend. It's this book that I've used called CMOS Circuit Design Layout and Simulation by Jacob Baker. And what I find useful in this book is chapter 7. So CMOS fabrication, if you go there, he explains basically how CMOS fabrication is done. So here you should basically read the FEOL and BEOL chapters. And BEOL is what we're going to talk about today. Right? The metal layers and the dielectric layers, essentially the parts that I used for passives. It's anyway a good book, I think, to kind of refer to once in a while, so you should have it. Okay, let's go back. Okay, so we're not really concerned with the FOX layer. I mean, this is inside the silicon substrate anyway. And then the polysilicon layer, also we don't care. Liner layer, also we don't care. The one we care about is this ILD, and starting from here, essentially. ILD all the way up to metal 1. ILD is interlayer dielectric, and IMD is intermetal dielectric. Okay, so I have another picture that I found online, which is sort of a very simple representation. So the FOX layer is typically inside the substrate, and then we have your ILD layer between the substrate and the metal 1, and then IMD 1, 2, 3, 4, 5, and so on. And then if you go back and look at the PDK, you see IMD 1A is the same thickness as metal 1, right? And the same for like IMD 2A and metal 2 and so on. And the reason behind that is that IMD 1A is this part and 1B is this part. Okay, so actually two different layers in this case. For different PDKs, they will also give you the exact elevation and thickness for all the layers, or they'll give you different layer thicknesses. So you don't really need to know what is IMD 1A, what is IMD 2, 1B, and so on, but I'm just mentioning that in this case. Okay, so we have all of the layers here. The metal layers are these ones, and so on. And then the dielectric layers are these, right? So what I've done here is I've basically copied all of the dielectric layers except the ones that we don't care about, which are these two, or I guess these three. The rest of the dielectric layers I've copied into this Excel sheet. So we'll see You can also look at it this way. So if you go to dielectrics, so the green stuff is what I calculated and the white stuff is what I copied. Actually, I do have the Fox layer. So I'm saying, okay, the dielectric thickness is 3,500 angstrom, then ILD is 3,000. Yeah, and ILD typically starts from the substrate, so that's why I have it. I don't really care about these two. These two are kind of embedded inside the ILD layer anyways. So, okay, so ILD is 3,000, and then I have the metal IMD1A, IMD1B, and so on. And you can look at this data. So essentially, I've just copied that over, and I've also copied down the dielectric constants of each of these layers. Okay, so once you have that, what we want to do is we want to combine I mean, when you do HFSS simulations, you don't want to have 100 different dielectrics. That can make the simulation too long. So what we would like to do is we'd like to kind of combine all these dielectrics into composite layers. So here I've combined from Fox to IMD2 into one layer, and then all of these into another layer, and then all of these into a top layer, and then the passivation. So you can combine these two passivations into one. I've actually separated them because this passivation layer had the same dielectric constant as the layers below it. So you can decide how you want to separate these. So I've done it in this way, where I have these in one layer, these in one, these in one, and this is a separate layer. Okay, so how do you actually calculate the thicknesses and the elevations? So this should say elevation. Oh. Of course, the elevation of the first layer is 0 because it starts from the silicon substrate itself. And then essentially you calculate the elevation of the next stage based on the thickness of the first stage. The thickness of this is the combination of the thickness of all of these, right? So you just add these up. That gives you this, which is what I have here as a macro. And then that gives you the elevation of the next stage. And then this is essentially the sum of all these guys. That plus this gives you the elevation of the next stage. And this is the summation of these guys. Okay, so we know how to calculate these two columns. Now we want to find out how to calculate the equivalent dielectric constant. And there's two ways to do that, right? So if I show you my notes, you can combine dielectric layers in series or in parallel, depending on which way the electric field is flowing, right? Or which way the electric field vectors are. So you can do, like, for example, a series combination. In this case, for example, if I have a parallel plate capacitor with two different dielectrics in series, so that's like one capacitor here, another capacitor here in series with it, and they have some epsilon value and some thickness, and the electric field lines are going straight down. Then you can use a series model for the series capacitance and calculate the equivalent dielectric constant. It's pretty simple. You have C1 and C2 in terms of the area epsilon1 and thickness. And we know that series combination of capacitors has this equation. And then you plug in the values and you'll see that the equivalent dielectric constant is given by this equation. Okay. And typically the dielectric, this model should be used for things like microstrip lines or patch antennas where underneath the patch or underneath the strip line, the microstrip line, the electric fields are normal to the dielectric layer. So this is usually the most widely used case. In some rare cases, you may also need the parallel combination where the electric field is along the dielectric layers, right? So again, here the thickness is now this way. So that's why it's in the numerator in the area factor. And the length, which is the height, I guess here is the same. So again, you can go through these simple equations to calculate what the equivalent dielectric constant is, because in this case now they are in parallel, right? And then the equivalent dielectric constant is given by this equation. So this is usually for a slot line or slot antenna. Maybe you want to use this, but typically I would use the series combination. That's what I usually rely on. And they're usually very close, the series and parallel combination, as we'll see, so it doesn't matter that much. But anyways, so you can use this equation, which is what I have done in the Excel sheet. So for example, you can see here I've made a macro to find the parallel combination and another macro to find the series combination. So you can go through that. It's pretty straightforward. I'll also upload this Excel sheet to my website. So under resources, you should, now it's not here because I still haven't finished, but I'll add a section here and upload this, the Excel sheet and also the HFSS file that we'll be using in this video. So you can grab both of them from here. Okay. I'll leave a link in the description to the website where you can find this Excel sheet. All right, so that's about dielectrics, is how I made this sheet, which we'll use now next. And then moving on to metals. If you go here and look here, it also gives us the thickness of each metal, M1, M2, and so on. And it also gives us the sheet resistances of each metal, right? So M1, M2, M2 to M7, M8 to M10, and M11. We don't care about the sheet resistance of these guys. And then also the sheet resistances of the vias are important. It hasn't given us the thickness of each via. We don't really need that because from the metal thickness and the location of the metals within the dielectrics, we know that, for example, M1 and IMD1A are at the same height and have the same thickness, which means that actually via 1 would be the same thickness as IMD1B, right? And here they also have a kind of schematic to show you what's going on. Right? So you have VR1, VR2, VR3, and so on up to VR10. Okay. So from this information, essentially, we can extract it. And that's what I've done here. So for example, I have metal thickness. The white ones are all the ones that I've taken from the PDK itself, and the green ones is what I've calculated. So let me reduce this. Okay. So we have metal thicknesses, and I told you that you can get the via thicknesses from the IMD values, right? IMDb values. Essentially, whatever is not the metal thickness is the via thickness, right? So that's where I've calculated these from. And once you have the thickness of all the metals, then of course the elevation becomes fairly trivial. And elevation of M1 would be the same elevation as IMD1B, which we already calculated here. Right, IMD1B has a thickness of 3000. We haven't calculated specifically the elevation, but the elevation is the thickness of ILD, right? Because that's what starts from the substrate. And that's why I have the elevation of the first metal layer as 3000. And then once you have this and this, then you can calculate this value, this plus this gives this, then this plus this gives this plus this gives this, and so on. You can populate all of these values. And then sheet resistance again directly comes from the PDK itself. So from that, you can populate these values. And to find the conductivity, again, there's a simple equation, which is also in these notes. Oh, I forgot to mention, there's a disclaimer in terms of the dielectric constant calculation. So the first thing that we assumed is that the effective dielectric constant is calculated assuming there is no infill. So infill is something that we'll reach when we do DRC, but essentially to maintain a certain metal density and to guarantee fabrication performance in any tape out fabrication process, they need to add some small metal pieces within the embedded inside the dielectric layers. So you can ask for infill exclusion, which we'll discuss later. But if you're not able to get an infill exclusion, you have to add infill into the dielectric. So in that case, there is a way to actually calculate what the effective dielectric constant would be when there is infill. And we'll discuss that in a later video. Essentially, you have to use these kind of PMC walls and do a quick calculation, quick simulation in HFSS. We'll do that later, but just keep in mind that the dielectric constant that we're calculating right now is without infill. And another kind of disclaimer, which is what I've noticed in my experience, is that typically the epsilon values that they give you in the PDK are good below 100 gigahertz. So at 10 gigahertz, they're usually measured at that frequency at 10 gigahertz. And then they're fairly constant, I would say, up to even maybe 100 gigahertz. Depending on the process, it may change. But above 100 gigahertz, the epsilon may start dropping. So if you're doing stuff at 300, 400, 500, or even 800 gigahertz, or even more, then you have to kind of keep this in mind that the epsilon value will change. So how do you know what the epsilon value actually is? The simplest way really to do it is to experimentally measure it yourself. You can't really find this information in papers and things like that because, of course, it's proprietary information for a given PDK. But you could experimentally measure it. We may discuss this in the future, but essentially you would have to fabricate a simple resonator on chip and then measure its S parameters, and from that extract the resonant frequency and the loss and the Q factor of the resonator, from which you can find the dielectric constant and loss tangent of the dielectric material. Okay, so with that in mind, we can move on to sheet resistance. And of course, a very simple equation that, resistance is rho L over A, where rho is the resistivity, and the sheet resistance is the resistance per square. So for a square, the length and width are the same, so you can cancel them. And then the sheet resistance then is given by resistivity divided by the thickness. So the thickness is typically constant. They mention what the sheet resistance is. And to find the resistivity, you just multiply sheet resistance with the thickness, and then from there you can get the conductivity, which is the inverse of the resistivity. Okay, so we'll need this bulk conductivity or conductivity of this of this metal when we move to HFSS, and that's why I'm kind of calculating it here. Okay, so of course you just multiply this and this, which is what I've done here. Product of these two times 10 to the minus 10, because this is an angstrom, right? And then I take the inverse of that, and that gives me the bulk conductivity. So I've done it for all of these. I would recommend, when you're actually doing this yourself, to hand calculate a few of these values to make sure they're correct. Okay, so now we've populated essentially this entire Excel sheet, for both the dielectrics and the metals. And we will use this to now draw stuff in HFSS and create the AMAT file. Okay, so to do that, let's go back to, so I've opened up a HFSS. I've already done it here actually, but let me maybe quickly show you how you can do it yourself. So open up HFSS. If you don't know what HFSS is, how to use it, I have some other videos on my channel that you can look at. But essentially, let's do a new file, insert HFSS design. So then I will go ahead and just draw some dielectric layers and metal layers. So I'll name this, let's say, metal 1, or just say M1. And then here I'm going to say minus M1 width divided by 2, M1 length divided by 2, and M1 elevation. So we'll make this 50 microns, and the elevation of M1 is, M1 elevation is 300 nanometers, right? Okay. M1 width, M1 length, and M1 thickness. And the thickness of M1 is 150 nanometers. Okay. So there we go. So we can do this for all, you have to do this basically for all the metal layers. The reason that we do this, or that I recommend doing this, so here I have all the metal layers and all the vias. So these are all the vias and these are all the metal layers. And I got all this information from this Excel sheet and I put it in, right? Just these two values really. The reason I recommend doing this is that when you do this, you'll see if you made any mistakes. So for example, sometimes the gap will not be matching, right? So you want all these vias to be touching the top and bottom and not extending beyond. So that's kind of why I do this. And once you're done with that, then you can do the dielectric layer. So here I've also added the silicon layer, which has an elevation of 0 and a thickness of 250 microns. Different processes will give you different silicon thicknesses, and that's typically not mentioned in the PDK as far as I know. So you'll have to contact the foundry if you want to know what this value is. You don't have to know, but it's sometimes important to know what this value is. For example, if you want to radiate into the silicon and then you want to put a silicon lens on the other side, then you should know what this thickness is. But if you ask if you send an email to the PDK folks or to the foundry, they should usually tell you what this value is. It's usually around 250 microns, give or take a few hundred microns maybe. Okay, so here I have silicon, and then I have the oxide. So let's take a look. So I'll hide the silicon layer. Oxide L, oxide M, oxide U, and passivation. And all of these values I've gotten from the dielectrics, right? So all of these, the elevation and thicknesses. Okay, so once you're done with this, then what I would recommend is to create the AMAT file. What you can do is just say right-click, assign material, and then we'll create some new materials here. So I'll say add material, GPDK 045, let's say M1. That's the M1 metal layer. And permittivity you can leave as 1. Bulk conductivity is what you want to change. So the metal layers, we only change this factor, and that comes directly from here. So the conductivity is, so I want to see the actual value. So what I'll do is number, click this and then say general. Okay. So the value here is now 905,797,10. So 905,10.14, right? And then hit OK. I've also already done this before for other metals, so that's why it's showing up already. I called it the wrong thing, but that's a good thing because I already had one called GPDK 045. Okay, and then I'll also show you for the dielectrics how to do this. So GPDK 045, let's just say temp. And let's say I want to do it for oxide L. And then for the dielectrics, you also need to change the permittivity. Typically, we also should have the dielectric loss tangent, but in this case, we don't have, and that's fine because typically the losses are dominated by the metals. So you don't need to actually put the loss tangent in here. And we know what the permittivity is of all these dielectrics now, right? So equivalent, we'll use a series combination. So oxide lower is this one, 3.345059. I'll just say 3.345 and then hit OK. All right. So I already have done this before, so I'm just going to delete the ones I just made. Okay. So you see that I have all of these metal layers in. When you do it the first time, it won't say personal library GPDK045, it'll just say project, and that's fine. But make sure you enter all of these values in, right? So check the values correctly, check these, and make sure these are inputted correctly. And once you have all of these set in, then you highlight all of them and then say export to library. Uh, oh, sorry. It's not doing it because it's already part of a library. Let me do this again. 5, let's just say temp. And I'll say M1, for example. And then let's just say the bond conductivity is E7. Yeah, so you see there's a project now, right? And a couple of more that we need to add are, so here I've called M1, metal 1, metal 10, metal 11, metal 111, 1, 2. So these two are composite metals. We've only done composite dielectrics so far, right? So composite dielectrics are when you combine dielectrics, but we also need to do composite metals. And calculating what the effective bulk conductivity for a composite metal is not actually that easy. In a future video, I'll talk about how to do that because in that model, you have to include the via conductivity as well. And to include the via conductivity, you need to know what kind of via density you can have. And that depends on the DRC rules. So once we go through DRC and LVS, then we will see how to make these kind of grids that we need for high frequency. And from those grids, we can extract what would be the effective bulk conductivity of composite metal layers. Okay, so having said that, so these two are actually composite metal layers, M1, M2, which will serve as a ground plane, and then M1, M11, which will serve as a sidewall, right? So for example, for grounded coplanar waveguides. You need a sidewall and a ground plane, right? So we'll use these two layers. M2, 3, 4, 5, 6, 7 is just for M2, M3, M4, since all of them have the same conductivity. I've called it like this. You don't have to call it like this. You can call it MX, for example. It's up to you how you want to name this. And then M8 and M9 are independent. They have their own dielectric constants. And then these are the oxide layers which we got. Passivation, and the silicon is the one that I added in, right? So you see when I add a new metal layer, it will show up as project. So let's add maybe another one. GPDK temp, and then I'll say 2, and then hit OK. All right, so you see that now we have these two which are project. So I'll click on these two. Now, when you do this, all of these will be project, and then you should select all of them and then hit export to library. It's not letting me do that, but that's why I'm showing these as an example. So when you click these two and then say export to library, it will tell you to create a new AMAT file. Right, so here, this is what I've done already. So I'll call this temp AMAT, and then this should be in your personal library. So within where your HFSS personal library is, that's where it should be. And then hit save, and then hit yes. Okay, and now you see that it has created a new personal library uh, for these two materials. So let me actually go ahead and remove these. And I also want to remove these. Okay. All right. So yeah, these are all the metal layers and the dielectric layers. So if you already have a okay, never mind. So let's actually go and take a look at what happened to the personal library file, right? So let me bring it to this. I have to copy paste it here. Just 1 second. I went into my personal library and I copied this file back here. If you open this, you'll see that now this will tell you the different layers that we've added in. Why is it not showing that? Okay, so this is what I originally made. I mean, if you do it correctly, basically with all the metal layers added in, and then export from the project here. Yeah. So if you select all of these when they're all projects and then export it to an AMAT file, the AMAT file should look, yeah, the AMAT file should look like this. So you see the layer name and then the conductivity values and which library it belongs to, right? So these are all for the different metal layers. So later on, when we actually find out how to find the composite metal layer uh, bulk conductivities, we'll come back in here and modify it for those two metal layers, which is this one, M1, M2, and then M1, M11, right? We'll change the conductivity value here. Okay, so that's how we generate the AMAT file. So this is a material file essentially. And you can transfer the AMAT file, for example, from one project to another and then import it as well. Example, like I will upload this AMAT file. You can take it and put it into your personal library, personal lab folder. And if you do that, then you should be able to access the materials directly. So you can say assign material, click on this, and then it should show up here. And then if you click on it, basically, then it will show you all the materials in that specific personal library. Okay, so that's about the AMAT file. The other file that we need to generate is, so let me actually delete this. We don't need this. So here I have, for example, all the dielectric and metal layers included. So I'll upload even this HFSS file that you can use as part of the resources on the website. Okay. So now that we have that, the last file that we need is the tech file. So in order to generate the tech file, you need this layer mapping file, and that is also in the PDK. So you can go into the PDK and then just say layer map, and then you should be able to find it. Right, so it'll tell you like what the layer name is, what kind of layer it is, what is the layer stream number, when you stream it as a GDS file, basically. And yeah, that's essentially what we need. We need these numbers, right? So, open up the layer mapping file and then create a new text file called .tech, or you can even just modify this file, which I'll upload onto the resources page. Change the name, of course, from GPDK to whichever PDK you're using. And we need to create, basically put all of this data in here. So this tech file will tell HFSS when it opens the GDS file. So essentially you go to Cadence, you draw these layouts, and then you export the GDS file. Now you want to import the GDS file into HFSS. But the problem is that in Cadence, everything is 2D, right? Whereas in HFSS, you need to tell it what each layer is in terms of what is its elevation and its thickness to make it a 3D file, right? And the tech file essentially tells HFSS how to do that. So it'll take a GDS file, it'll take this tech file, it'll combine, it'll tell you, okay, in this GDS file, the layer number is 7. It'll say, okay, for layer 7, HFSS should call it M1. It should give it this color, it should give it this elevation, and it should give it this thickness. And that's how HFSS converts a 2D GDS file coming from Cadence into a 3D model file in HFSS. So in the next video, we'll actually do an example with this, but in this video, I'm just showing you how to create these files. Okay, so what we need to do is open up this layer mapping file. So I'll open it as a separate file. And then we need to compare it to this tech file. So what I've done here is I said, okay, M1, where is M1, right? Make sure you use the drawing layer of M1 because there's also a pin layer and the slot layer. Go to M1 drawing, which is this one. And the layer number is 7, right? And that's why I've called it 7 here. And then M2 is 9, and it's 9, and so on, right? VO1 is 8, so you go to VO1, and that's 8. And okay, so that's about the metal layers. We'll come to this later. So once you have the layer number, the layer name, the color, and there are hundreds and hundreds of colors that you can use. If you want to know what the color values are, you can just go online and say, I found it on the HFSS online, one of the HFSS online help manuals. You can see the different names of all the layers and so on, right? So you can put any color that you like. So this is the HFSS online help file. Okay. Yeah, put a color name and then the elevation and thickness, which we calculated in this Excel file, right? The elevation and thickness in nanometers. Here it's in angstroms, whereas here we want it to be in nanometers. So I put all that data in here for every metal layer, right? Every metal layer and every via layer. What's the elevation and what's the thickness? I also put in comments what the conductivity is. You don't really need to put that there, but typically I usually like print this tech file and have it, handy on like a wall next to me or something like that. So I can quickly look at it when doing layouts. And at that time, it's kind of useful to have this conductivity value in here as well. And that's why I have it in comments here. Okay, so that's about the metal layer. So that's pretty straightforward. All of it comes directly from the Excel sheet and from the layer mapping file, this file. And then for the dielectrics that we made, for the composite dielectrics, we need to use some dummy layers because Cadence doesn't have these layers already in there, right? So the dummy layers that I'm using here is cap dummy, resistance dummy, BJT dummy, NPN dummy, and PW dummy. You can pick whichever ones you want from all these dummy layers, ones that we're not going to use in our high frequency layouts, and choose those numbers to be, for example, silicon. So when we go and do Cadence layouts, if you actually want to do a layout for these, what you can do is you can use these layers instead, these layers to represent these. And that's also why it's useful to have this kind of printed out. So for example, if I want to use an oxide U, then instead of oxide U, I will do a layout of BJT dummy so that when you export it to HFSS, HFSS thinks that actually layer 15 is oxide U, right? With this color and this elevation and this thickness. Okay, so that's how you do this. And I've also included two special metal layers, which is the M1, M2 and M1, M11. These are the composite metal layers, which I talked about. And here I'm using ESD dummy and DIO dummy as the dummy layers for these. Okay, so that's how you make this tech file. Once you have this tech file ready, just save it and keep it in handy in some location because we need to use it when we go from Cadence to HFSS. Okay, so that's about how to create kind of the AMAT file and the TECH file. Sometimes people also use the ABC file, but I've noticed that you don't really need that. In fact, for my personal preference, I don't even actually use these values or the dielectric layer values. I do use these, but I don't use these because you don't really need them. What you can instead do is just import all the metal layers and these via layers, and we will import all of these. We can just copy paste all the dielectric layers from this HFSS file because I made all of it parametric. So for example, you can change the width and length of all the dielectric layers, right, in these parameters. So that's kind of that's my personal preference. But we'll do an example and see how to do all of these going back and forth between different layers. Okay, so with that, maybe I'll conclude this video. So here we've seen essentially how to make the AMAT file and the TECH file from the PDK. That's pretty much all that we've done. In the next video, we'll actually do a layout in in Cadence of like a transmission line, for example, and then export it to HFSS and then use these layers to actually make a 3D model of it. Okay, thank you so much. Have a nice day. See you in the next one.